Good to see you all. Hope you're all doing okay, hanging in there in the midst of life in 2020. Yeah, certainly not a boring weekend by 2020 standards even. But hope everyone is doing all right. The plan for today is to just wrap up a couple of things relating to material in chapter 6, Laplace transforms, that won't be on this exam that you have on Wednesday, and then we can use the rest of the time to review for the exam. So I just want to let you know, we'll get into this shortly, but the exam is going to be administered same exact way as the last one. So there'll be a handful of multiple choice questions you'll do on a quiz on Canvas, and then there'll be a written portion that you upload afterwards. The solutions to all of the homeworks have been uploaded into Canvas as well. So even this last one that you handed in this past week that hasn't been returned or graded, you can check your work with the solutions at least. Okay, so let's first just kind of talk about some of the material that you looked over on the reading quiz before today. And then I want to just talk about a couple of more properties with Laplace transforms. So we'll have a really good foundation to go with after the exam to get ready for our third exam. So the third exam is just going to be on this content with Laplace transforms. So on the reading quiz, you had to calculate or give some Laplace transforms for various functions. So depending on what problems you were given, the quizzes were slightly different for different people, but you were randomized some subset of these 5 problems on your reading quiz. And so the idea here is you just want to be sure that you read things carefully, that there will be some questions that say, use the definition, derive the Laplace transform, and then you would want to go through that process that we went through last week. Others will just say, using the table and properties, find the Laplace transform. And that's what I was asking for these problems. So for these problems, you wouldn't need to set up an integral. It's very much like using, if you ever used like the table of integrals in calculus, same sort of idea here. And that is we kind of look at our function, we look at the table, which one does it look most resemble? It looks like this one. So here's my formula, and that's it. So for this one, it's pair we would get by looking at this one over here. So our value for A here was 7. And we do want to specify the domain here for all of these Laplace transforms. And then these trig functions, sine and cosine, they look very similar, but they've got something different going on in the top. So you just want to be sure you keep those two straight. For the sine, we would get f of s. Our value for b is 3. So we would plug a 3 in over here. We plug a 3 in over there. And that domain is s bigger than 0. And then for the cosine, same idea, except now we have an s on top. So that would be the difference in the Laplace transform of sine and cosine. And then for these power functions, we can use this formula over here. And so in this case, we've got n equals 2. So we would have 2 factorial over s cubed, right, which is 2 over s cubed for s bigger than 0. And similar idea for this power function, except now the power is 3. So we would get 3 factorial over s to the 3 plus 1 for s bigger than 0. Okay, any questions? So these are, if you can identify the form, you've got the table there. Hopefully they're not too technical. You should definitely expect to see a number of these on that last exam. But like I said, you also should be able to derive some of these. And in particular, that piecewise function that we did on one of the worksheets last week, you'll see something like that. So you'll have one more homework assignment this semester. Just so you know, that'll be on Laplace transforms. That will be to help you get ready for the exam. So there'll be some problems on that homework that are going to ask you to use the definition and some that you can use this table. Okay, any questions? So far what we've been doing with Laplace transforms is we derived a bunch of these formulas, at least the first bunch over here, and some of these table properties. So we did these two properties, and we did this property last time. We did L3 last time, which basically tells us that when we multiply by an exponential, that is equivalent to shifting the Laplace transform. And that's where these formulas over here come from on the table. So there's two more properties that I want to talk about, and then we can move on after the exam and think about how we can apply these to solve differential equations. So the really important one that we're going to need to consider next is what happens, how is the Laplace transform of the derivative of a function related to its Laplace transform itself. One of my L's got messed up here. That should be the fancy Laplace transform L. So this is a really important property that we're going to need when we're going to be working with differential equations, because we're going to need to know how do I take the Laplace transform of the derivative of something. But any questions before we take a look at that property?
So you're saying we're taking a Laplace of a derivative, or we're taking a derivative of a Laplace?
Okay, so this property, again, we're on worksheet 21, this was. So last time we did this property, the shifting property. And so we're pretty much over here at question 3, where we want to prove this property about how do we take the Laplace transform of a derivative. And so one little definition that we're going to need in order to prove this result in question 3 is what it means for a function to be of exponential order. And so what exponential order of a function means is it's basically telling us what is the power of the exponential function that is bounding the function itself. So in other words, what is an exponential function that this function is guaranteed to be less than? So I think the definition itself maybe is a little bit more technical than we need to think about, but we can kind of illustrate this with some examples. And that is, if I were taking a look at this function, we would say it has exponential order 7 because for large values of t, it's going to basically behave like e to the 7t. That cosine part isn't really going to be all that significant. And something like this, not all functions have exponential order because this function over here grows faster than any function of this form over here. So basically, it's a way of saying that this function is going to be less than an exponential function with power alpha. That's what it means to be of exponential order alpha. Okay, so let's kind of take a look at how this proof would go. So what I would like to do, so what we have is we have some function f, and we know that this function has a Laplace transform. So maybe we know what its Laplace transform is. And we want to find a formula for the Laplace transform of the derivative of f prime. So we're going to start with the definition. So I'm going to plug f prime into the definition, right? So this is the definition of the Laplace transform. Just plugging in f prime for a function instead of f, which we usually have. And since this is an improper integral, then we've got some limit that we want to take as the upper limit goes off to infinity. And so the trick with this proof is I want to integrate something that looks like e to the minus st times f prime of t. And so this is a good candidate to use integration by parts on, because we are taking the integral of a function times the derivative of a function, right? And that's really great setup for using integration by parts. So we could define u as the e to the minus st. And we've got b prime as f prime. And then with integration by parts, we can then put it into this form. So this is like our uv minus the integral of u prime v.
I just have a question on that. Why is u
So the
prime?
uv term is e to the minus st times f of t, and the u prime v is minus 1 over s e to the minus st times f of t.
Why is u
Okay,
prime?
so the short answer is to prove this, we need to use integration by parts. Any questions? So then let's think about what happens for each of those two terms. So this first piece over here, right, this is our uv term. So we don't have to integrate this, but we need to evaluate this at the limits of 0 and n as n is going to infinity. So evaluating this at 0, right, I would get e to the 0 times f of t. So that's where we're getting all of this from. I think I have an extra negative sign for some reason. Right, so when I plug in 0 for this one, I'm going to get 1 times f of 0, and this is the lower limit, so we subtract it. And then for the upper limit, we need to think about what happens as n goes to infinity. And so for this integral over here that we still have to evaluate, right, I can pull that minus 1 over s out because we're integrating with respect to t, so that is a constant. And then let me just write this as an improper integral again. And does anybody recognize what this is?
The definition of a Laplace.
It's the Laplace transform. Can you hear us?
I see Kyle waving. I don't know if that's at me. We can't hear you. You're on mute, Kyle. Can you guys hear me? Yeah, okay. So this thing that I circled in green, what does that look like? What can we call that? Should look familiar. Time's ticking away. Oh, I see. There's lots of things coming in. Oh, you are trying. Oh, can you guys not speak to me? I don't.
I don't think you can hear us.
Yeah, can hear.
I can hear you.
And
Yeah.
Well, it's a Laplace transform.
Thank you. Yes, that is a Laplace transform. Maybe I think I just had my thing on mute, sorry. Okay, problem solved. Sorry if I missed anything else. Apparently my computer was on mute. Yes, so this is by definition the Laplace transform of f. So this piece over here is the Laplace transform of f. So what we can see here is that if I want to take the Laplace transform of f prime, it is going to depend on what the Laplace transform of the original function f is. So there's some relation there.
Why is u prime -1 over s? Shouldn't it just be negative s if it's u prime?
Oh, we would take the derivative of this. Yeah, thank you. That should just be a minus f.
Okay. Okay. Cool.
So let me fix that. Yeah. That would look like that. Yeah. Okay. Any other questions about that part so far? So if we're kind of keeping score with what we're hoping to get, this term matches that term we were hoping to get in f0 somewhere. And we have an s times f of s, so that seems to match up with what we have over there. And the question is, well, like, what do we do with all of this stuff over here? We hope that that goes to 0 because we already have all the other terms that we want. And so to take a look at this limit, we're going to use the fact that we have assumed in this statement that the function f and f prime, they both have exponential order alpha. So when I'm trying to calculate this limit over here, let me just kind of come, that's what's happening down here, right? One thing that we can say is, in general, this step is fine because, right, the limit of the absolute value of something is always going to be greater than the limit of that thing itself. And then going from here to here, we're using the fact that f of t is of exponential order alpha. And so what that means is for large values of n, this is going to be less than some constant times e to the alpha t. That function behaves like e to the alpha t. And so it was this exponential order assumption that allows us to get this limit bounded, and therefore, if this piece is bounded by some exponential function, then the resulting limit, we can group our terms over here, and we know that this is going to go to 0 as long as the power of the exponent is approaching a large negative number. So this is going to go to 0 as long as s minus alpha is positive. So to kind of regroup all of that stuff down here, that one goes to 0. That gives me an s of 0, and this one over here was, by definition, the Laplace transform of lowercase f. And so that gives us our result that we were hoping to get as long as we have this condition that S is larger than alpha. Okay, any questions?
Yeah, just go back up to a couple of rows up
Mhm.
where you have the limit, it's that last part of the limit there that you have circled in green.
Mhm.
How did you replace n with t there, the lowercase t?
So let's see. Over here, we are saying that f of n, so sorry, this should be an n over here. You're right. And this should be an n over there. Yeah. Because our variable here is n. So yeah, we're going to put an n over there.
Okay.
Any other questions?
So because f of t is of exponential order alpha, the function c e to the alpha t is greater than f of t, f of n for big stuff.
For big stuff, that's right. And that's all we care about here is big stuff. Yeah.
And then what is exponential order again? Does it have to have e to the alpha t in it?
It just means that the function is, for large values of its input, the function is going to behave like an exponential function of power alpha t.
So like would t work like if it wasn't cosine 5t but like just like regular t, and if there wasn't an e to the 7t, could we still say it has exponential order?
Say that again. So you want to calculate the exponential order of what function?
Of something without e to the 7t. Does it have to have e to the
So you can think about, here's a function f of t. What do you think its exponential order is?
e to the t?
Yeah, so this function is less than e to the t for large values of t, right? For small values of t, that's not true. But for large values of t, that is true. So yes, you could say that f of t, that this function over here has exponential order 1, for example.
Okay.
So it's just saying this function is going to be bounded by what exponential function.
Gotcha.
Yeah, and like I said, not all functions have this property. So this result over here only applies to functions like this. We can't use it on functions like this.
And then
So-
yeah, go.
So for an exponential order, do we know if it's going to converge or diverge, or this doesn't tell us?
Yeah, this is going to converge because I can replace f with this function, and then we can find values for s that are going to guarantee that this thing goes to 0.
Okay, thank you.
Yep. So I think we're getting a little bit lost in the weeds with this exponential order definition. Certainly, we need it in this to get this proof. But what ultimately I want to make sure we're comfortable doing is being able to apply this proof, apply this result. So now we can use this to calculate the Laplace transform of a function if I know what the Laplace transform of its antiderivative is. So for example, if we know this, and we want to find this, we can use the fact that that these two functions are almost related directly by this derivative relationship. But if I know that cosine, if I'm going to let say cosine of b of t be f of t, since f of t is going to be the function whose Laplace transform I know. Okay, so that's given over here. So how is sine of bt related to cosine of b of t? So this is not the correct formula. What would I need to tweak about that? So if f of t is cosine b of t, then what would I get if I took the derivative of that?
You would get a b in there. So you'd have like, if you took the derivative of cosine, you'd have negative b sine bt. Yeah.
So we have minus b over there. That's right. So here is what we know. So I know that L of f of t, which is, we're calling f of t the cosine function. We know that this is s over s squared plus b squared for s bigger than 0. And what I'd like to do is figure out what this is. And so using this property, I can find a formula for minus b times the sine of bt. And from this previous step, we knew that this was equal to s f of s minus f of 0. So in this case, our f of s, capital F of s, is exactly the Laplace transform of this. So this is the s over s squared plus b squared. And then we would subtract f of 0 from that. And again, our function f is right here. So what do I get when I evaluate this at 0?
1.
Yeah, 1, right? We just get cosine of 0, which is 1. So if I simplify all of this, what I get is I'm going to write this over common denominator. So I've got an s squared over s squared plus b squared. And then I also have this minus 1 right, that I could add those two expressions together, putting them over a common denominator of s squared plus b squared. So what I get here is the Laplace transform of minus b times the sine of bt gives me minus b squared over s squared plus b squared. The s squareds cancel out. So we've got minus b squared over s squared plus b squared is the Laplace transform of minus b times the sine of bt. But we didn't want to have that minus b inside of there. What I can do is multiply both sides of this equation by minus 1 over b to account for that constant. Okay, and that gave us the desired result that we have already discussed on that table. But that's one way that you could verify that result. And so this step where I'm going from here to here, remember that these Laplace transforms have the property that we can move constants inside and outside. Okay, any questions? Okay, so then just to take this out one step further, because we're going to be using this process of Laplace transforms to solve differential equations of order 2, or we can even go higher. So it's going to be useful to know how to take the Laplace transform of higher order derivatives as well. And so this is a really great place where you can use proof by induction. So I know that I'm teaching Math 3000 and we're like exactly at that point in the course. So for anyone that's seen induction, this is a great place to try and practice that process, since I don't think everyone here has taken Math 3000 or is familiar with that. I won't get into that, but we can see how we could use the result for the first derivative to at least prove the result for the second derivative. And this will give you a sense for how this works for any power derivative. So what I can do here is I want to calculate the Laplace transform of the second derivative of f. So what I can do is I can think of right? Let me just call some function g to be the first derivative of f. Okay, in which case g prime would be the second derivative of f. And so if I want to take the Laplace transform of g prime, I could now use the result that we said we know how to do this for first derivatives, namely that's the formula up top. So I'm going to get an s times the Laplace transform of g minus g of 0, right? Just using that result that we have up there, where capital F, right, represents the Laplace transform of lowercase f. So here we have a g instead of an f. Now let me replace all of these g's in terms of what they are in terms of our original function f. So those g's were all f primes. And now we can use that result again, right? Since we've already proven this for first order derivatives. So this I can replace with s times the Laplace transform of little f minus f of 0. And that's our result. Oops. So that gave us a formula for the second derivative. Okay, where we actually didn't use anything other than the fact that we already have proven the first case. And so that's why this sets up for anyone that's familiar with how the induction process goes. This is very much a great scenario to apply induction to get the general result. So if you've seen induction before, this would be something good to practice. If you haven't seen induction before, just know that I could then use this result to prove it for the third derivative, and then use the third derivative to prove it for the fourth derivative, and so on. So in general, we now could use this property to help us solve differential equations of any order. We're usually going to stop at the second order, but we could go further. Okay, so just to kind of catch us up with where we're at, that handles property L4. And we've got kind of one more property to talk about. We can talk about this one after the exam next time. So let me just say for Monday, after the exam, I'll put up a little video about this property and just have you not prove this property, but on the reading quiz, apply this property to calculate Laplace transforms. So then when we come back after the exam, we'll be ready to hit the ground running with Laplace transforms. Okay, any questions? Okay, well, then we've got an exam coming up, so I imagine you might have some questions on that. So I just want to comment quickly, like what is the content on the exam to make sure you're clear with what material is on the exam, and then we're welcome to go through whatever I can do to help you. So this exam is on the material that we covered in chapters 3 and 8. We didn't cover every section in those chapters in the reading material, and we did some additional stuff that was not actually in that material, like null clines and stuff like that. So I think more safely, it's better to kind of base this on like what stuff did we do in worksheets 14 through 19. And that relates to the last 3 or 4 homework assignments, last 3 homework assignments. So kind of worksheet 14, that was our kind of initial rabbit and fox problem, and it was just thinking about how can we read differential equations and identify what type of competitive cooperative species we might have, how we can approximate solutions visually in the plane, and how we kind of numerically approximated them from the formulas for dr dt and ds dt. So kind of that worksheet was kind of a big tour through all of the ideas that we pretty much went through in more detail in the future sheets. So worksheet 14 was kind of, here's the big picture. And then we kind of broke that big picture down into smaller chunks. So in worksheet 15, that was all of the work that we did with like approximating long-term behavior of solutions using null clients, X and Y null clients. And you have a problem on the review stuff of practicing this. So it's finding these null clients and then being able to sketch them in the phase plane and then be able to use those sketches to say what type of stability the equilibrium might have. So we did all of this equilibrium stability analysis without using the linear algebra at first. In worksheet 16, that was mostly working with systems, linear and nonlinear at that point. But rather than finding solutions for X and solution for Y separately, we first talked about how we can write out phase plane equation right, which was dy dt over dx dt, and how we can solve that. That's a first order differential equation. So that means you might need to use separation of variables. You might need to use integrating factor to solve that phase plane equation. So just keep that in mind. So to solve this, you might need to use separation or possibly integrating factor if it's not separable. And when you find these solutions, let me just say they tend to be implicit. Might not be, but they tend to be things that look like, you know, you can't solve for y, and that's okay in those cases.
With the phase plane equation, we didn't do much other than just describing what it does, right? After we get the phase plane equation, it would be interpreting it, right?
Yeah, so there were some where you were asked to sketch a couple of typical phase plane solutions. So maybe they were like circles. I think there was one where you had like, yeah. So beyond solving them, yeah, you should be able to sketch them if you're able to recognize what their graphs look like.
Like with ellipses and everything, we need to be familiar with what that might represent.
Yeah, I would say there were some cases where you were asked to actually sketch some of the phase plane solutions, yeah. And when you're sketching things in the phase plane, what's really important is that you put arrows on your curves to indicate the direction that you're moving along those curves. Okay, worksheet 17, we spent a bit of time on that. So that was linear systems and the way that we first thought about solving those. So now we're no longer finding phase plane solutions, but we're finding general solutions for X and for Y separately. And the first way that we talked about doing this was writing the system as a matrix equation, finding the eigenvalues for the matrix of coefficients, and then finding the general solution for X, plugging that into the differential equation, and then finding the general solution for Y. So let me just say that this did not involve any eigenvectors. So in particular, if you're solving a linear system where you have complex or repeated roots, you're definitely not going to want to go the eigenvector route, since those eigenvectors are going to be really complex to find when you have complex roots. So you don't need to do that. Regardless of whether your eigenvalues are real or complex, you can use them to find one solution and then substitute that solution into the differential equation to find the other solution. Okay. And then we talked about stability of equilibrium, in this case, the origin, when we just have linear systems. So when you have a linear system, this means you're only going to have one equilibrium at the origin. And we want to know whether that equilibrium is stable or unstable. Well, then what we do is we find the eigenvalues, and based on the sign or whether they're real or imaginary, we have all of these different stability types. So definitely being able to say, these are my eigenvalues, therefore the origin is going to be this type of equilibrium is certainly important. And in the case when we had two distinct real eigenvalues, this was the case where we could find the eigenvectors and then sketch an approximate solution in the phase plane. So worksheet 18 was all about how we can interpret eigenvalues, what they tell us about the long-term behavior of solutions that start near the origin. And then the last thing we did is we just said, well, let's just take these same ideas and apply them to nonlinear systems. So if we want to look at stability of equilibrium for nonlinear systems, then what we did is at each equilibrium, we approximated the differential equation with a linear system, and then we found the eigenvalues and did the same analysis for those. So when you're going through this process, I would certainly encourage you to kind of use that Jacobian method that we talked about the last couple weeks. And so these last two worksheets were a lot of what your last homework assignment was on. And so that hasn't been graded, so you haven't gotten comments on that yet, but you can check your work with the solutions that were posted up online. Are there any questions? So I kind of received two questions by email that I want to answer. They're probably somewhat related to each other. So somebody asked about the stability analysis for the pendulum problem that we didn't do together in class that I put up online. And somebody else asked about the rabbit fox problem that was on your homework assignment that you had to hand in. And I think those are both very, very much similar to each other. So let me start with those at least, and then if there are other questions in addition to that, just let me know. So let me open up the solutions to that last homework assignment. Okay, yeah, so this was the homework that you guys had for last week. And so the very last problem was a rabbit and fox problem. And the differential equation looked like this. So kind of the first step is to find the equilibrium. And so the equilibrium here, there are three of them in this one that you should have found. At the origin, R starts off at 400 and we have no foxes, or R is 100 rabbits and 30 foxes. And at least I think the question that I received on this was not necessarily how to find the equilibrium, but and are there any questions about that process? And you can kind of see here that there is work to show. So when you're doing this on the exam, don't skip all the stuff that's in blue and just give me the stuff that's boxed in red, but be sure to provide the supporting work to justify that. Okay, then we would want to classify each of these three equilibria. So what we do is we kind of consider this function like f of RT, and we think of this function as, here I have f of Rf, right? I'm thinking of this as a function of R and F, and this is the function that we typically call G. So we calculate partial derivatives for F with respect to R and with respect to capital F. We do the same for G. And here is what the Jacobian would look like in general. And then we can evaluate the Jacobian at each equilibrium point. So I'm going kind of fast, but I suspect that you have thought about this already. Maybe you don't have your work with you there, but are there any questions about that? So we take all the partial derivatives, and then for the equilibrium at 0, 0, we would evaluate them at R equals 0, F equals 0. So lots of stuff go away. And at 0, 0, here's the resulting Jacobian. And so from that, just be sure that when I'm asking you, and I will, like, tell me what the linearization is at this equilibrium, you don't just tell me the Jacobian, but you're able to write it as a system of differential equations. And from this, we get one positive, one negative eigenvalue. So that means that the origin is a saddle point. Then we can do the same at 400, 0. We get a slightly different matrix that has slightly different eigenvalues, which might change the type of equilibrium that it is. But that one also is a saddle point.
I know this isn't really the point, but when you do the P of lambda there, would you have a +4 at the end?
You would have -4 times 0, right? So
right.
that would give you like a -0 at the end. Yeah.
Okay. Thanks.
Yep. And then there's this other equilibrium that's right in the middle of quadrant 1 at 130. And when you linearize that one, the eigenvalues are really not nice, but they're complex. And what you should be able to identify is that they're complex and the real part is negative. So when you have complex roots with a negative real part, that's when you have a spiral sink. And so the question that I got was mainly like, how do we piece all of this together to draw the picture? So I think, and you guys are welcome to ask me to go back and check over any of this other stuff, but at least how I understood the question was, okay, I understand the linearization and how to classify these points, but how do I draw the picture when I have 3 different equilibrium points? And so the picture is down here. And so we had 2 saddle points at the origin. Here's the other one that was at 400, 0. That's the one that's over here. And then we have one at 130. And so let me just say, I didn't show the work here, but it's actually pretty, this is easy to find the eigenvectors, relatively speaking, for this one. And that this has 2 eigenvectors for the equilibrium at 0. One of them is like the vector 1, 0, and one of them is the vector 0, 1. So you could find the eigenvectors and plot the phase plane near that point using those eigenvectors. So at the origin, you have one vector is like 0, 1, and the other vector is like 1, 0. And so the vector 1, 0, that's the one that has the positive eigenvalue. So that's why those arrows are going away. And the vector 0, 1, that's the one that has the negative eigenvalue. So it is the one that's going in. So what I would do is I would take this system over here if I wanted to, and then find the eigenvectors. Right, the same way that we did for our linear system, I could draw them over here and then draw the corresponding arrows in the right direction based on the sign of those eigenvectors. And now I can see that things would look like this. And this just kind of tells me what happens close to 0, 0. So it is possible that if I start off on this axis that I actually would head directly in towards the equilibrium at 0, 0, but otherwise I'm most likely going to start to head away from that equilibrium eventually. And then you can do the same for the other saddle point, which is it has 2 eigenvectors for each of the eigenvalues, and you can plot those. So one of them would just be the vector 1, 0, and the other one is some vector that has some negative slope. So that's where this black line came from. But I can draw the 2 eigenvector directions and then put the arrows on those directions, and we have a saddle over here. So I could draw what nearby solutions look like. And at the point at 130, that was a spiral sink. So we're not going to find eigenvectors for that because they're complex, but I know that it spins in. And the question that I would want you to consider when you're doing this is a spiral sink can go in like this, or it can go in like this. So it can spin counterclockwise in, or it can spin clockwise in. And so you need to determine that. And the way that you can do that is to just pick a point close by and use the differential equations to determine whether dr dt is positive or negative, or df dt is positive or negative. So for example, I can think about what happens at the point 131. And just to make that point, right? So that would be close to the equilibrium, but just 1 unit above it, right? And I can evaluate what are the RDT and the FDT when I plug in 131. And when you check this out, actually, R equals 100 is a null cline. So the FDT is going to be 0. But what you'll see here is that the RDT actually is negative. And so that's why at that point, we see that we're not moving vertically at all, but we're moving to the left just a little bit. And that's what tells me I'm rotating around in that direction. And again, these values of 0 and something negative, I got from coming back, way back to these equations over here. So all I did is I said, if I plug in 100 for R, this is going to be 0, so there's no vertical component. And if I plug in 100 for R and 31 for F, this actually gives me something negative. So that's what tells me we're moving to the left. So kind of the question that I got was, well, we have all of these different equilibrium and we have different eigenvectors at each equilibrium. How do I represent the eigenvectors on this plot? Well, the eigenvectors are only going to be sketched in at the equilibrium where you found them. So the eigenvectors that I found for the equilibrium at 0, 0, where they don't have any effect on what's happening over here. And then I just put together a little description of what's happening based on that picture. So basically, what's happening in this picture is, unless we're in one of these really special situations where we start with no rabbits or no foxes, we're going to head to 130. So if we have some positive amount of rabbits and some positive amount of foxes, as time goes on, we're going to approach 100 rabbits and 30 foxes. But if you happen to be in one of these special situations where, for example, you start off with some foxes but no rabbits, then that's kind of a special situation. Or if you start off with rabbits but no foxes, that's another special situation. Okay, so does that help answer a question? So though, I know that person who had a question on this is here, so please just let me know if you have any other questions about that one. Okay, and so let me take us over to the pendulum question, since somebody asked about that one. So this is worksheet 19. When we did this one, and so those we did together, did this together. Yeah, and so here was the part that we didn't do together. So this was the stability analysis for the pendulum. And so I don't know what the particular question was about this, but I'm happy to go through it. So Christine, I think this was your question. Was there something in particular about this that you wanted to talk about? Was it finding the equilibrium, the stability, or sketching the picture, or all of that?
It's that part where you say that the sine of theta is approximately theta. So if you do that, then you know you can get rid of sine of theta, you just replace it with theta. So when I did that on the practice problems, I basically got a sinc for anything I put in because it didn't really depend on theta.
So we don't want to replace sine of theta with theta everywhere. And so I think what you're referring to is what we did way back over here when we first took a look at this, before we knew how to linearize things. And we were saying, okay, if I want to think about what is happening at the equilibrium, at the origin, then we can replace sine of theta with theta. Because if we're going to come up with the tangent approximation for the sine of theta, and we do this at the origin, the approximation is the line, you know, y equals theta. But back at the very end, we didn't use that. We just used the linearization process to deal with the equilibrium here. So I found the Jacobian and then used the Jacobian at each equilibrium.
Yeah, I did that, and like I put in pi and 0, and I got it was a sinc, and it shouldn't have been a sinc.
Yeah, so the partial derivatives for this, I don't know if I wrote out the general Jacobian, but we would take the derivative of that with respect to theta, which is going to be 0, and then we would take the derivative of that with respect to v, which would give us 1.
Mhm.
And then we would take partial derivatives of this. So we take the partial with respect to theta first, and that gives me minus the cosine of theta. And then this gives me minus 0.2. And so when you evaluate this at, say, you know, something odd times pi, well, the cosine of like 3 pi, that's minus 1, right?
Mhm.
And so if k is odd, then I think I just did the, so here's the even one over here. But if k is odd, then what that would look like be 0, 1, minus a minus 1, and a minus 0.2. So when you have an odd one, the cosine is actually negative, so you have a negative times a negative over here. So in the case of k being odd, your matrix looks like this, and that gives you 1 positive and 1 negative eigenvalue, as opposed to when k is even, you have a negative 1 over here, and that gives you imaginary eigenvalues that have this negative real part, and that's why that was a spiral sink.
There was like a term in front of the sign in the one on the homework though, and I ended up getting like 2 real solutions for that, like for the pi. And yeah, pi 0 if k is 1, odd. Yeah, I don't know. Like it just canceled out under the square root because I had to use the quadratic formula and it ended up being 0 under the square root. It was like 4g over L minus 4g over L. Yeah, it was weird.
Yeah, but so that's why you're getting the difference in stability for the even and the odd ones, is because the Jacobian is different values when k is even versus k being odd. Yeah, if you have I thought the question was about this one. If it's about something that was on the homework, I could take a look at that separately. Okay. But so is there, what other questions can I help you guys with? Whether it's specific or general? All right. Well, then I will leave you guys to your to get ready. Well, good luck studying. Yeah, and for Wednesday, you know, same instructions. Just get on Zoom a little bit early with your cameras on, and if you can show up 5 minutes earlier, so we can just make sure that all the links are open and you're able to see everything correctly, so we get all that stuff ironed out of the way. And then you can plan to work until about 3:15. And if you need some extra time to upload your exam after that, you can take some extra time. That's okay. But otherwise, if you do have any questions as you're getting ready, I have office hours tomorrow from 1:30 to 2:30. Yeah. So you're welcome to pop on Zoom tomorrow. Otherwise, I'll see you guys on Wednesday.